Okay, welcome to the 11I notes on similar figures. Okay, rocky start. We'll see if we can get better. 11I notes on similar figures. We're going to go through this. I will tell you that I need you to do this page first. Okay, this page right here and this page right here. I need you to do those first. They're really self-explanatory. They're very simple. It'll take you no more than 10 minutes. But those red boxes that you see, those are both theorems that you need to figure out on your own to have a better understanding of what we're about to do. I'm going to reference those as we go, and you can try to follow along without doing them, but I'm telling you right now, pause the video. Take the 8 minutes and do this on your own so that you have an understanding of what is going on. All right? First, let's start here. Similar figures are two figures that have the same shape, but are different sizes. Similar figures have congruent angles and proportional sides. That's, I think, a key right there. We need to understand that similar figures have congruent angles. Angles are the same, but the sides are proportional. What does proportional mean? It means having a constant ratio to another quantity, and when we say ratio, we should instantly see the word fraction there just in our brains. All right? So let's take a look. Let's determine which of the following figures are similar, and we're going to justify our answers using proportions. Okay, so here's what I mean. I'm going to compare, since we know they have to be the same shape, let's start with, shapes that are the same. We'll start with this cylinder here. 42 is the height and 56 is the radius. The only other cylinder that has a radius that is bigger than the height is this one. So let's compare those two. 42 and 56. I want to see if this ratio is equivalent to the ratio that exists here. If it is, then these are similar. So in my calculator, I'm just going to put in 42. I'm going to use the fraction button, 56, and I get 3/4, and then 36, and the fraction button, and I get 3/4 again. So I know now, based on that, that these two are similar. Okay. Let's work on the other two cylinders. Okay. Let's say we have 100 over 77, and does that equal 40 over 28? Okay, let's go into our TI this time. So we'll go into 100 divided by 77. You can use decimals also. 40 divided by 28. I get two different decimals. What that tells me is that these two are not similar. Okay, so this is not similar to that. Let's take a look at our pentagonal prisms. Pentagonal pyramids. Okay, so here we have 28 over 12, and we want to know, does that equal 70 over 27? So let's go back in our Casio. This time I'll do decimals here too. 28 divided by 12 gives me 2 1/3. 70 divided by 27 gives me 2 point blah 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 blah. Doesn't matter what it is. It just matters that they're different. Okay, because they're different, that is not similar to that. And lastly, we have our square pyramids. Okay, so 21 is the height and it's the side length. Here, 49 is the height and the side length. I don't even need to set that up. The height and side length are the same. Because they're the same, I know that those two are also similar. Okay, so there we go. So those two are similar also. Easy enough. So from that sheet that I asked you to do, if two figures are similar with a ratio of A to B, the ratio of their perimeter is also A to B. And the ratio of their area is A squared to B squared. Why is that important to know? Well, it makes these problems very simple to do. If the figures have a ratio of 3/4, the ratio of their perimeter is the same. It's 3/4. Okay, that's easy. If we have a ratio of their area, then we just take those two numbers and we square them both. So if 3/4 is the perimeter, then 3 squared is 9, and 4 squared is 16. So the ratio of their area is 9/16. Okay, easy enough. Now we're going to use this concept by setting up these proportions every time. Okay, we're going to set these up every time, and we're going to put in the information that's given to us in the problem and then see what we can figure out. So here's what I mean by that. The area of a regular octagon is 45 centimeters squared. What is the area of a regular octagon with sides 6 times as large? Well, sides, that's A to B. So 1 to 6. And then I square both those. So this is 1 to 36. That's the ratio of the areas. So because I'm being asked about the area of the large one, I'm going to use 1 over 36. And I'm going to set it equal to 45 over x. 45 was the smaller of the two. So it goes on top because 1 is smaller than 36. So 45 times 36 and that's 1620. So really easy there. X equals 1620. Two trapezoids have areas of 847 and 700. So 847, that said area. That's what they gave us. So that's where I'm going to put it. 847 to 700. Now the first thing I want to do is I want to check to see, and I'm always going to do this first. Really important here. I'm going to check to see, does that reduce? So 847, fraction button, 700, and look at that. It does. It reduces to 121, 100. 121 and 100. Now you can do that, by the way. I know we've talked about this. You can do that in the TI also. If I put 847 divided by 700, I get a decimal. But if I hit math, enter, enter, it changes it to a fraction for me. Okay. Now I can go backwards to find the perimeter ratio, which is 11 to 10. Really easy, and there's my answer. The setup each time is what's important. I mean, you'll notice that on every single one of these problems, this a to b, a squared to b squared, I write it every time. The widths are 3 to 20. Well, that width is the same as the perimeter ratio, so that's done. And the area, well, you just square them both. That's all there is to that problem. That's it. Here, on the right side, it says find the ratios of the circumferences and of the areas of the small circle to the larger one. Well, this 6x here is the length of this radius. So that's 6x, and that's 8x. And when we reduce 6x over 8x, we actually get 3 to 4. Okay? 3 to 4, I already know the answer is D because it's the only option. But just to prove the point, we square them both, and we get 9/16, and the answer there is D. Easy enough. The setup is what's really important, you know. This furthers along our setup, and this looks familiar if you did that page I asked you to do on your own. The ratio of the surface area is a squared to b squared. The ratio of the volume is a cubed to b cubed. So now we're going to use this setup with all three. Okay, let's see what they tell us here. They tell us that the areas of corresponding faces is 81 and 144. And then they want to know what's the side length, what's the perimeter, and what's the volume. What are those ratios? Okay, so I'm really important here, okay? I'm going to always check to see if the ratios can be reduced. Always, always, always. All right? So let's go in our calculator and check to see 81 and 144, and then again, math, enter, enter, and if I'm using a TI, and I get 9/16. So it does reduce. 9/16. I take the square root of that. To go from a squared to a, you just take the square root. Square root of 9 is 3, square root of 16 is 4. That is the ratio of the side length. That is the ratio of the perimeter. To find volume, I cube them. 3 cubed, 27. 4 cubed, 64. And that's it. Okay. It's the setup that's really important here. Here we have surface area, so they're giving us area again. So 196 to 676. I'm going to check and see if that reduces. I'll do this one in my Casio, 196. Then I'm going to use the fraction button, 676. And that reduces to 49 and 169. And then here the square root of 49 is 7. The square root of 169 is 13. And then I'm going to cube both of them to get this ratio. 343 and then 13 cubed. 13 cubed is 2197. Now it says, what is the volume of the smaller one if the volume of the larger one is 2197? Well, that should look really familiar. 343 over 2197 equals x over 2197. Well, hey, what do you know? X is 343. Okay. Here, they're asking us, what are two potential surface areas if the volume ratio is 64 to 729? Okay, so first, every time I'm always checking, does it reduce, does it reduce, does it reduce? I want to know because it matters. This one, it doesn't. So now I'm going to take the cube root. In the Casio, that is shift left parentheses, 64, and the cube root of 64 is 4. We always have to go back to A to B first. On a TI, I'm going to hit math 4, and then the number, and the cube root of 729 is 9. Square both of those, and I get 16 to 81. Only one of these choices has the same ratio as 16 to 81. If you double 16, you get 32. Double 81, you get 162. 16 over 81 equals 32 over 162. It doesn't equal that, it doesn't equal that, and it doesn't equal that. It equals that one. Okay? And lastly, again, you'll notice every time with this setup is the same. Okay, every time. The diameter here on this one is it says how much does another sphere weigh? If its diameter is 8 times as large, so this is 1 to 8, this is 1 to 64, and this is 1 to 512. Weight is volume, so I'm going to say 1 over 512 equals, and we have the smaller ones, that's 0.9. We're looking for the larger one. So then I'm just going to multiply 512 times 0.9, and I get 460.8. Easy peasy there. And then on this one over here, I get a balloon that's 2 centimeters wide that holds 71 centimeters of air. And I want to know how much air has to go into it for the design to be 4 centimeters wide. So that ratio is the A to B. So 2 to 4, and then I'm going to reduce that. So it's 1 to 2, which is then 1 to 4, which is then 1 to 8. Okay? So now I'm going to use this 1 to 8. And when it was small, it was 71, and when it's large, I don't know it, and I get x equals 568 when I cross multiply, and the answer there is A. Hope you enjoyed the notes. Hope you did the part that I asked you to do on your own. It's really important. We have a daily check next time on working backwards. See ya.